Today's lesson will be the first of three on the concept of acids and bases. Now, we will start with an introduction. We will consider two different models of acids and bases. Then we will look at the concept of strong acids and bases. Then concentrated and dilute acids and bases. And finally, we will look at the meaning of conjugate acid and base pairs. So let's get started. We all know acids and bases in our everyday lives. Acids, for example, are in many of the foods that we eat, including tartaric acid in wine, citric acid in citrus fruits, and even in our stomachs, we have stomach acid that help us with digestion. Other acids, such as sulfuric acid and nitric acid, we would find in the laboratories. Even our drinks, such as our fizzy drinks, contain an acid called carbonic acid. Acids have the property that they are corrosive. In other words, they can make metals corrode, or they taste sharp. It's a very interesting taste that acids have. On the other hand, bases are also part of our everyday lives. And we will find bases mostly in products such as soaps, in cleaners, and even in fertilizers. So one of the main fertilizers is ammonia, and that comes in the form of nitrogen that is produced by the Haber process. But this is not what we want to understand acids and bases by in the scientific context. That is the purpose of this lesson today. So here in this table is a list of a number of acids and bases. This is not the list of all the acids and bases that are available, but these are important ones for you to understand. So this first acid, acetic acid or vinegar, has the chemical formula CH3COOH. Citric acid occurs in lemon juice with the formula H3C6H5O7. Hydrochloric acid, the formula HCl. Sulfuric acid, the formula H2SO4. And nitric acid with the formula HNO3. On the side of the bases, we have sodium hydroxide, or NaOH, known as caustic soda, used in products like drain cleaner. Ammonium hydroxide, NH4OH, ammonia, NH3, and bicarbonate of soda, baking soda, NaHCO3. So these are a few of the acids and bases that we can encounter in everyday life. But how can we define acids and bases scientifically? There are a number of models for describing acids and bases, and we will consider two in this lesson. The first is the Arrhenius definition for acids and bases. And Arrhenius was a chemist in the 19th century, and he said that acids form this ion, H3O+, or hydronium, when they are dissolved in water. And what they do is they increase the concentration of the hydronium ions. So if you look at this diagram over here, we can see here that green circle represents your chloride ion, and the white represents a hydrogen or a proton, and the red here is an oxygen atom. And so what this is, these atoms here, these are water molecules, two hydrogens and one oxygen. And you can see here, if you look at this one over here, you've got a chloride and a hydrogen for the hydrogen chloride. So what happens when the acid dissolves in water, you form this sort of ion over here. So there you can see there's an ion with one oxygen and three hydrogens. And those are your hydronium ions. And according to Arrhenius, the concentration of these ions is increased when these acids are dissolved in water. So if you look at this picture over here, which is a simulation of the acid in water, after a little while, you can see that there are more of these hydronium ions that have formed as the chloride and the hydrogen have acted and reacted with the water. So here you can see two lone hydrogen ions, or known as protons, and this is also in the solution. They just have not had a chance to react with the water yet. So this is what it means by increasing the concentration of the hydronium ions. On the other hand, Arrhenius said that a Arrhenius base forms hydroxide ions, or OH minus ions. And the definition says that an Arrhenius base increases the concentration of hydroxide ions in solution. So if you look at this diagram here you've got some water, and here you have a base, something like sodium hydroxide. So this round gray sphere, this represents your sodium, and these two, that's your hydroxide, your oxygen in red and your hydrogen in white. So this is before it mixes, and you've got your sodium hydroxide and the water. And what you notice here is that the hydroxides, so these ions, have now been freed. When the sodium hydroxide reacts with the water, you can see there's an hydroxide ion, another hydroxide ion, another hydroxide ion. So initially, there were no hydroxide ions. They were all collected and attached to the sodium. But now we can see that these hydroxide ions are now free and in the solution. And so this shows you how an acid can be considered to be an base can be considered to be an Arrhenius base. This definition only works for acids and bases that are dissolved in water. And so a more advanced formulation of an acid and base model was produced by two scientists, and together their model is known as the Bronsted-Lowry model of acids and bases. So here's the Bronsted-Lowry model. So according to the Bronsted-Lowry model, an acid is a substance that donates or gives away its protons. And the protons are just a hydrogen ion, in other words, a hydrogen atom that has lost its electron, while a base is a substance that accepts protons. It takes the protons from the acid. So if you look here, this is an HCl, hydrogen in white, chloride in green. This is the sodium hydroxide. And what's happened is you can see that in the second image, the chloride has given away its proton. That proton now sits over here, and the chloride then joins with the sodium to form a salt in the form of sodium chloride. And the product of this reaction is the water molecule that is shown here. Another example of this is for the reaction of HCl with ammonia. This is ammonia, nitrogen in blue, hydrogens in white. And you can see here that this proton has been donated by the chloride, and it's attached to the ammonia molecule, and this forms what's called an ammonium ion. And the formula for ammonium is NH4. Because there are 4 hydrogens and 1, and the charge of this is positive because it is an ion. So the charge of the proton is positive, and so that charge is then transferred to the ammonia, and it forms an ammonium ion. Examples of the Bronsted-Lowry acid in solution would be the following. So if you look at this here, you can see you've got the formula for hydrochloric acid, HCl. It is in solution in water, so the state symbol is AQ for an aqueous solution. When this reacts with ammonia that is dissolved in water, you can see that the ammonia becomes ammonium. It has a positive charge, and you have a chloride ion that remains in the solution. If we look at each reaction separately, we can see here the HCl then loses, it splits into a proton and a chloride ion, and then this proton will be accepted by the ammonia to form the ammonium ion. Because the HCl donates a proton, this is the donation of the proton shown here, that means that it is the acid, while the ammonia accepts the proton, as you can see here, and therefore this is the base. In terms of the Arrhenius model, a similar discussion can be made. So the HCl dissolved in water increases the hydronium concentration, and therefore, according to the Arrhenius model, hydrochloric acid is the acid. Sodium hydroxide in water splits up to form sodium and hydroxide ions. And so because sodium hydroxide in water increases the concentration of hydroxide ions, this is a base. Remember that Arrhenius model only applies to acids and bases dissolved in water. Now, water is a very interesting substance because sometimes it can act as a base and sometimes it can act as an acid. So when we look at the following reaction here, we've got this is acetic acid, CH3COOH, which combines with water. What happens is the hydronium concentration increases and we remain behind with a CH3COO minus ion. If you look at it separately, we can see that this CH3COOH ionizes. In other words, remember CH3COOH is a covalent molecule and it splits up into these ions. So CH3COOH is said to ionize in water. So there are these protons that are now in the water. The water then can react with the proton to form a hydronium ion in this solution. So in this case, the water has accepted a hydrogen ion or a proton and has formed a hydronium. So because the water has accepted a proton, it is a base, according to the Bronsted-Lowry definition. Water can also act as an acid. So look at the example of ammonia dissolved in water. Water splits up into hydroxide and a proton. Again, water is a covalent molecule, so it ionizes, it forms ions to form hydroxide and hydronium ions. And this hydroxide ion, this proton, will then be added to the ammonia and will form an ammonium ion. So in this case, what has happened is that the water has donated a proton. And in terms of the Bronsted-Lowry model, acids donate protons. So in this example, water is the acid. And this brings us to a definition of an amphoteric substance. So what is an amphoteric substance? It's one that can act as an acid in one reaction or a base in another reaction. So water is an example of an amphoteric substance. This is a very closely related definition, and that is the definition of amphiprotic. So if you split this up into two words, we can see the amphi. It's the same as the amphi in amphibian. An amphibian is an animal that can live on both land and water. So it has two places where it can live. In the same way, an amphiprotic substance has two kinds of reactions. Protic, this is from the word proton, so it will have two types of protons. It can donate a proton in one reaction, or it can accept a proton in another reaction. Acids that release only one proton called monoprotic. Mono means one, and protic refers to protons. So monoprotic means one proton. And if we look at something like HCl, it only has one proton. An acid that can release two protons, like sulfuric acid or H2SO4, this is diprotic. Di means two, and we can see here in the formula that there are two protons in the sulfuric acid. Any acid that can donate more than one proton is called polyprotic. So poly means many. So polyprotic acids can donate more than one kind of one proton. The next concept that we will look at is that of a strong acid and a strong base, and the opposite, a weak acid and a weak base. So let's look at the definition. So a strong acid or a strong base is one that almost completely dissociates to form ions in solution. When a substance is covalent, it will split up into ions, and we call that process ionization. When a substance is already ionic and dissolved in water, when it splits up, we call that process dissociation. So something like hydrochloric acid, HCl, is a covalent substance, so it will ionize. Something like sodium hydroxide, the base, is a ionic substance, and we say that the sodium hydroxide will dissociate when in solution. But what do we mean by completely dissociates? So let's take a look here. Here on the left-hand side, we have the acid. So this is some kind of acid molecule, call it HA. H for the proton, because acids have protons, and A, that's the other ion that's attached to it. So in the case of HCl, this would be a chloride ion. In water, what happens is this now splits up into the ions from the negative side, and the hydrogen goes and attaches to the water and increases the hydronium concentration. And if you look in here, you can see that this is what the molecule looks like. And in here, you can see that there are none of these molecules are left. All of the molecules have split up or ionized to form the negative ion and the hydronium ion. And if you look in here, you can see it's completely dissociated. Because there are such a large concentration of these ions and they are positively and negatively charged, we can see that if we put a light in, we can get a very bright light that comes out because there's a lot of charge that can be transferred in the solution. Similarly, for a strong base, the same sort of thing happens. You've got a metal ion, for example, so sodium being a metal, and a hydroxide ion. And what happens is that this completely dissociates. And if we look in the solution here, we see that there are none of these molecules in the solution. They've all been split up into their different ions. Something else to notice, which will become apparent, is this arrow to show that the equilibrium of this reaction goes one way. This is not a reversible reaction. So, very important to understand, you can say that it almost completely dissociates. Now, practically, there will always be a very small concentration of your original molecule or ionic substance in the solution, but because the equilibrium lies very far to the right, and this is a concept we'll revisit, this is not the case. Now let's look at a weak acid and a weak base. So for a weak acid and a weak base, only a small percentage of the molecules will either ionize or dissociate to form the ions in solution. So if we have a weak acid here, this is an example of a weak acid, we can see that this is what the weak acid molecule looks like, and there are still plenty of weak acid molecules left in the solution. Only a few of them have formed the hydronium ions. So compared to the previous diagram, there are very few hydronium ions in the solution, and therefore this is a weak acid. We can see here also that the equilibrium arrow points to the left and to the right, which means this is a reversible reaction. Similarly, with a very weak base, the same thing happens. If you look at this, this is the base particle, molecule, only in one. You can see there are lots of these base particles still in the solution, and only very few of them have formed hydroxide ions. And therefore, this is a weak base. And there is a list of strong acids and strong bases and weak acids and weak bases, and you should be able to explain how they dissociate and how they ionize. We can also see that the brightness of this light bulb in both these cases is much less in these weak acids and bases than they were in the strong acids and bases. And the reason is that these ions, which carry the charge, there are very few of them in the solution. And that's an indication of a weak base or a weak acid. The next concept, which is related but not the same, is that of the concentrated or dilute acids and bases. First of all, we will look at the idea of a standard solution. The standard solution is very important when we do experiments with acids and bases, especially titrations. And a standard solution is one where the exact concentration of a solute in a solvent is known. So a concentrated solution is one where there is a high ratio of dissolved substance to the solvent. So this is the same for acids and bases. If you look at this image on the right here, this is an example of a concentrated solution. You'll see there are many particles in this solution. So there are a large number of the dissolved substance particles in the same amount of solvent. In this case, could be water. A dilute solution, on the other hand, is where there is a low ratio of dissolved substance to the solvent. As in this example, you can see there are many fewer particles in this solution than there are in this solution. And that's the difference between a concentrated and a dilute solution. Don't get confused. A strong and a weak acid and base is not the same as a concentrated or dilute acid and base. You can have a dilute strong acid, you can have a concentrated weak acid, and the opposite is also true. Finally, we will look at the concept of the conjugate acid and base pairs. Now, if we look at this example here, we've got nitric acid, HNO3, and we have some base. It's not important which specific base it is, but the fact that the base contains hydroxide ions is what's important here. Now, what we notice is as this reversible reaction occurs, the products of this reaction on this side would be your nitrate ion and water. Now, look what happens here. The HNO3, which is an acid, it has donated its proton. Its product no longer has a proton. The OH minus has accepted the proton to form water. So because the acid donated its proton. That's the definition of the Bronsted-Lowry acid. And the OH accepted the proton. That is the definition of the base. Because this reaction is reversible, let's consider what happens when we go from right to left. So when reading this reaction from right to left, what will happen? We'll notice that the NO3 minus is going to accept a proton from the water, and that will form the HNO3. While reading from right to left, the water is going to donate a proton to the NO3. And therefore, reading from right to left, the water acts as an acid and the nitrate acts as a base. And therefore, we can call this nitrate ion the conjugate base of the nitric acid. And we can also call the water the conjugate acid of the base, the hydroxide. Conjugate acid-base pair, per the definition, contains two compounds that differ only by a hydrogen ion and a charge of +1. And look at this. HNO3, that is an acid. The conjugate base has lost its proton, but they are together, and the HNO3 is a +1 charge removed from the NO3 minus. Similarly, the water is the conjugate acid to the base of the hydroxide, and again, the water has one more proton than the hydroxide, and the hydroxide is 1 minus and the water is neutral, so the charge difference in both cases is +1. Let's look at another example. If we look at this reaction between H2SO4 and a chloride ion, so the H2SO4 can donate one of its protons. So this is the acid because it donates a proton. This is the base. Because the product, if we read from left to right, the product HCl, the chloride ion has now accepted a proton to form HCl, and the HSO4 minus has lost a proton from the H2SO4. So, if the H2SO4 is the acid, then the HSO4 minus will be the conjugate base of that acid. Because reading from right to left now, this HSO4 minus will accept a proton from the HCl to form our H2SO4. So that's the conjugate base of the H2SO4, and the HCl is the conjugate acid. If you look at the HCl in solution, what's going to happen is that the HCl will donate its proton to the HSO4 minus, and therefore it will be the acid, and that will then show us that for reading the reaction from right to left, the HCl acts as an acid and the HSO4 minus acts as a base. Thank you very much.